This video will focus on the role osmium could play in quantum computing, and the implications for the osmium market as this new source of potential demand comes online. Although quantum tech feels like science fiction, it might be much closer to mass adoption than we realize, as mega technology corporations and some of the brightest minds in academia are working together to develop quantum computers that could eventually become as commonplace as personal computers are today. Osmium also shows great promise in the field of modern medicine, currently being studied for use in anti-cancer agents, medical implants and coatings, and as a catalyst in the creation of certain pharmaceutical drugs. In the world of military technology, osmium is also starting to gain attention, and its use is being considered for durable coatings to protect critical components in jet engines, naval equipment, hypersonic missiles, and more. So how could osmium play a key role when it comes to quantum computing? And how could it impact this already rare metal's supply-demand dynamics? Let's dive deeper to find out, starting with the basics. A platinum group noble metal discovered in the early 1800s, osmium's rarity means that only a small amount is extracted each year, and this number is starting to dwindle as ethical sources become more and more scarce in an increasingly divided world. Osmium is a truly unique precious metal, being the rarest stable element known to humanity with the greatest density of all the elements, along with possessing some truly incredible characteristics. A reflectivity unlike any other metal, an extremely low vapor pressure, and a very high melting point. The crystallized and purified version of osmium, achieved through a closely guarded secret methodology that took a small group of Swiss scientists 4 decades to master, is taking both the jewelry and tangible investment markets by storm. And recent developments point to osmium's potential importance in quantum computing, an exciting technology with implications that could totally transform our world. Quantum computing harnesses the powerful laws of quantum mechanics, superposition, entanglement, and interference to perform calculations impossible for classical computers. Instead of relying on binary bits, locked in rigid states of 0 or 1, quantum computers use something called qubits. These qubits can exist in multiple states at once, intertwine across distances, and process vast complexities in parallel, unlocking unprecedented speed and precision. Osmium, with its extraordinary density and unique quantum properties, including extreme spin-orbit coupling and strong electron correlations, could be a game changer in the realm of quantum computing. Recent breakthroughs reveal its potential for high-temperature superconductivity under pressure, opening doors to revolutionary quantum applications. In fact, osmium is already being called the silicon of the quantum age, a nod to that element's integral role in manufacturing the semiconductors and computer chips that dominate our modern computing reality. Let's explore some recent research to uncover the facts about osmium's role in quantum technology. Starting back in 1993, a pivotal study conducted by chemists at the University of London found that by bonding osmium with organic molecules, they could create luminous compounds that absorb and emit light with remarkable efficiency, their electrons dancing in excited states for microseconds, an eternity in the quantum world. These unusually long-lived photon states, achieved through osmium's unique properties, could be ideal for quantum repeaters, the backbone of a future quantum internet, a quiet breakthrough that turned the spotlight on osmium as a potential key to the quantum computing future that lies ahead. In research published in the Nature journal in 2023, scientists from the University of Tennessee, Oak Ridge National Laboratory, and the University of Louisville discovered that lithium osmium oxide, a combination of high-purity osmium oxide and lithium carbonate or lithium oxide, forms a quantum spin liquid, a rare state where electron spins remain in constant fluctuation, defying conventional magnetic order. This chaotic quantum behavior isn't a flaw, it's a feature, one that could lead to ultra-stable qubits resistant to decoherence, which is the process by which a quantum system loses its properties due to interactions with the external environment, the primary obstacle to building practical quantum computers. While osmium's platinum group metal's cousin iridium has long been a focus of quantum research, osmium's stronger spin-orbit coupling makes it a more compelling candidate for next-generation quantum materials. Perhaps even more exciting, although more theoretical, is research from Cornell University, speculating that a compound called osmium hydride, formed through a combination of pure osmium powder and hydrogen gas under immense pressure, could become a superconductor, effortlessly channeling electricity without resistance. This prediction suggests that at temperatures near minus 440 degrees Fahrenheit, colder than deep space, this ultra-dense metal might unlock perfect conductivity, thanks to quantum maneuvers only osmium can pull off. But there's a catch. Osmium hydride has never been successfully created outside of computer models, due to an array of complications that haven't yet been overcome by the scientific community. However, if this puzzle is solved, osmium hydride could achieve superconductivity for quantum circuits, the quantum equivalent of classical computer circuits, and quantum sensors, devices that exploit quantum states to measure physical quantities with unprecedented precision. Ultimately, osmium's most compelling characteristics in the field of quantum technology are strong spin-orbit coupling, electron correlations, and potential superconductivity, which addresses the two major hurdles currently faced in quantum tech: stability and precision. With that being said, we could just be scratching the surface, and universities and labs are racing to develop osmium-based quantum materials, including the Max Planck Institute, currently studying osmium's electron correlations for topological quantum computing, and Ohio State University, who are collaborating with national labs to test osmium hydride superconductivity in diamond anvil cells. The quantum osmium party is just getting started, and with so many brilliant minds converging to advance the field, the possibilities seem truly limitless. While researchers worldwide attempt to solve the challenges of using osmium in a variety of quantum applications, the greater challenge still may lie in the difficulty with sourcing purified osmium to meet this new high-tech demand. Meaningful sources of osmium are exceedingly hard to come by. In the past, South Africa was the most significant producer, having been one of the world's main sources of osmium in the 1970s. Since then, however, production from that region has fallen, and today, its output is almost irrelevant, a shadow of its former capacity. Although Russia has also been a notable producer, sanctions currently in place take it off the list of ethical sources, making the question of securing osmium supply even more precarious. At present, only 17 cubic meters of osmium are estimated to still exist in the Earth's crust, and of this, only a few kilograms per year can be economically extracted. Furthering this lack of supply is the fact that the majority of the above-ground osmium is held by Osmium Institutes for use in crystallization for the jewelry and tangible asset markets, meaning this osmium is off-limits for quantum tech purposes, barring perhaps much higher prices. We are currently seeing a race in artificial intelligence, as countries and companies around the world compete to bring the most efficient and advanced products to market. Quantum computing could completely alter the AI landscape, and those involved are well aware of this fact. As osmium's use in quantum tech continues to advance, the effects on the demand side could go parabolic, putting an absolutely epic squeeze on osmium supplies. As the supply-demand dynamics play out on a global stage, the price of osmium could be pushed to levels previously thought unimaginable, adding an extra layer of potential upside for those holding physical osmium as a tangible investment vehicle. And in case you think all of this is still far off in the future, at this very moment, Companies and national labs are aggressively filing patents to lock down intellectual property around osmium's quantum applications, signaling its potential to disrupt industries from computing to energy. American tech giant Honeywell, whose business revolves around aerospace, industrial automation, and energy, have joined forces with Cambridge Quantum to form Quantinum, the world's largest integrated quantum computing company. Quantinum is currently working to patent osmium complexes for quantum sensors, as well as the integration of those osmium complexes with Honeywell's trapped ion quantum computers. Meanwhile, on the other side of the globe, Tanaka Precious Metals, a Japanese manufacturer of precious metals materials, with a focus on electronics, semiconductors, and the automotive industry, is seeking patents for osmium thin films and the stabilization of osmium hydride phases for high-pressure superconductivity applications. Tanaka has already secured a Japanese patent for osmium-based superconducting layers in 2022, a clear sign that they believe osmium's future in quantum technology is bright indeed. So what could all of this mean for the osmium market as a whole? Let's attempt to uncover the possibilities. Until now, osmium's role in both the jewelry and tangible asset investment markets has been steadily growing. As the rarest and most luminous precious metal, crystalline osmium is making massive waves in the high-end jewelry sector, as evidenced by the recent Gem Geneve 2025 event in Geneva, where the Osmium Visionary Contest was held. The contest invited the brightest minds in the jewelry design field to bring all their creativity to the table in crafting innovative osmium jewelry pieces that could redefine the future of the luxury jewelry market. Hundreds of designers took part in the contest, with results that can only be described as breathtaking. And before you think that osmium-focused jewelry is a trend that has yet to catch on, consider that prices for osmium set watches have already reached north of 400,000 euros, with rings, necklaces, and earrings regularly demanding prices of 5 figures or more. As a tangible investment, osmium is playing an ever-increasing role in hard asset portfolios, as its built-in scarcity and proprietary certification system in the form of the Osmium database proves its quality and authenticity, in addition to its ownership, incredible advantages that have drawn comparisons to Bitcoin by enterprising investors. In addition, osmium is starting to carve out a role for itself in modern medicine and is increasingly being considered for cutting-edge military technologies. Osmium complexes show great promise as an alternative to platinum-based chemotherapy treatments for cancer, due to reduced DNA damage risks. Osmium nanozymes are another recent development, potentially reshaping the landscape in targeted drug delivery and real-time disease monitoring. In the high-stakes world of advanced military technology, osmium's extraordinary wear resistance makes it a prime candidate for the most demanding applications, from precision bearings in turbine blades of advanced aircraft to thermal coatings that shield hypersonic vehicles from the blistering heat of Mach speeds. While still too rare and costly for widespread use, osmium's unique properties could potentially carve out a critical niche in the future of defense, where even the smallest advantage can tip the scales. With nuclear energy on the rise, osmium is also being studied for potential use in molten salt nuclear reactors. Osmium's exceptional pressure and corrosion resistance could make it useful as a protective coating for reactor components, and its other unique properties leave open possibilities for specialized applications in next-generation nuclear systems. As we can see, osmium already had a lot going for it before massive technology companies and scientific institutions started to take interest in the metal for the purpose of developing quantum technology. And now this additional layer could really take the market to a whole other level. How long will it be until sovereign nations start to catch on to osmium's importance in the quantum field? Could we see osmium eventually declared a critical mineral as the race to master the quantum space intensifies and geopolitical rivalries spark a competition for the future of computation power? These are certainly fascinating questions to ponder, and when we consider that 1,000 tons of platinum ore is generally required to extract only 3 grams of osmium, and the real lack of any meaningful supply of the metal currently in the Earth's crust, the possibilities for the price of osmium and its applications in our quantum future appear to be incredibly intriguing.